Hello students, welcome to JP's Academy and I am Nitin sir. In today's lecture, students, we are going to complete chemical bonding in 30 minutes. So before we start the lecture, I want all the students to quickly like, subscribe to the channel and share it with your friends. Let's get into the lecture. So we start with what exactly is a chemical bond. A chemical bond, students, is a force which holds together the atoms in a molecule. Basic से अगर हम start करें, so there are three types of chemical bonds जो हम इस chapter में पढ़ेंगे, जिसमें students the first type which is electrovalent and ionic bond हम last part of the chapter में करने वाले हैं, and the first and the most important focus of the chapter will be covalent bonding. There is one more type of bonding, student, जिसे हम बोलते हैं coordinate bond or dative bond. What is, student, electrovalent bond or ionic bond? Bonds formed by mutual sharing, pardon me, transfer of electrons. Covalent bond is formed by mutual sharing of electrons. Coordinate bond is when there is one donor and one acceptor. A coordinate bond, students, once formed is more or less a covalent bond. Next, students, we have Lewis octet theory. Now students, in the first part of the chapter we will try and understand how molecules are formed, what's the reason their stability and what are the different theories behind it. So सबसे पहले people we have octet rule, and octet rule हमें क्या बताता है students, that atoms can combine by transferring their electrons and they will keep doing this. They will transfer electrons या उन्हें हम share करेंगे till the point we have 8 electrons, till the point they have an octet in their valence shell. Now, using Lewis octet theory, students, we need to first understand how do we use this theory to draw structures. These are the rules that I have written, students, to draw Lewis structure. And इसे हम एक example लेके करेंगे, हम carbonate ion लेके, students, will try and understand how to make Lewis structure. So सबसे पहले, students, what we will understand is we need to add all the valence electrons in the combining atom. तो यहाँ पे हमारे पास है कार्बन. कार्बन के number of valence electrons are 4. Oxygen, number of valence electrons in oxygen is 6. So CO3 2 minus में number of valence electrons, students, हो गए 22. But यहाँ पे हमें एक चीज पे ध्यान रखना है. So the charge here is -2. Whenever there is a negative charge, or for anions, students, each negative charge means you will add 1 electron. So यहाँ पे since दो negative charge हैं, 22 में हम 2 और ऐड कर देंगे, नंबर ऑफ वैलेंस इलेक्ट्रॉन्स यहाँ पे हो जाएंगे 24. Had it been a cation, students, तो आप क्या करेंगे, you will reduce the number of electrons. Next step, after counting the number of electrons, what we do is हम एक basic skeleton बनाने की कोशिश करेंगे. In the skeleton, students, remember that the least electronegative atom will form the central position, will occupy the central position. So for example, over here, जैसे कि कार्बन हमारा least electronegative था, तो हम बीच में कार्बन को प्लेस करेंगे and then we will place the remaining electronegative oxygen atoms. So ये skeleton बनाना, people, कभी कभार एक guess work भी हो सकता है, but we need to take a proper guess as to which atom should be placed where. Students, इसके बाद वाला step is the most important step, where what we will do is we will assign the valence electrons. In this case, we got that as 24. We will assign the valence electrons to all the atoms in the molecule in such a way that सारे atoms के octet complete होने चाहिए. That is what we observe here. So ये 24 electrons properly divided हैं in such a way that each atom present should have a complete octet. Students, once you draw the Lewis structure, next important point जो हमें याद रखना है is that we calculate something called as formal charge. Formal charge का मतलब क्या होता है, students? It is the difference between the number of valence electrons of that atom in an isolated or in a free state and the number of electrons assigned to that atom in its Lewis structure. Formal charge calculate करने का एक simple सा formula है, students. Total number of valence electrons in the atom, subtract the number of valence electrons in that atom, and again subtract half the number of बॉन्ड और शेयर्ड इलेक्ट्रॉन्स। तो यही जो CO3 2 माइनस है उसका एग्जाम्पल लेके वी विल ट्राई एंड फाइंड द फॉर्मल चार्ज इन एवरी एटम विच इज प्रेजेंट। सो लेट्स स्टार्ट विद द फर्स्ट वन। अगर ये हम ऑक्सीजन एटम देखें स्टूडेंट्स, तो हमें पता है ऑक्सीजन एटम में नंबर ऑफ वैलेंस इलेक्ट्रॉन्स आर 6 माइनस नंबर ऑफ नॉन बॉन्डिंग या लोन पेयर इलेक्ट्रॉन्स। अगर मैं इस ऑक्सीजन पे देखूं स्टूडेंट्स 1 2 3 4 5 6, there are 6 lone pair electrons and minus half into the number of shared electrons. This oxygen and this carbon के बीच में I see 2 electrons which are being shared. इसे हम सॉल्व करें तो हमें फॉर्मल चार्ज मिलता है ये ऑक्सीजन एटम पे -1। एक और एग्जांपल ले लेते स्टूडेंट्स। फॉर एग्जांपल ये कार्बन पे वी वांट टू कैलकुलेट द फॉर्मल चार्ज rules. The first formula is total number of valence electrons, so that is 4 minus number of lone pair. स्टूडेंट्स यहाँ पे दिख रहा है हमें lone pair electrons कोई नहीं है तो -0 minus half into number of shared pair, 2 यहाँ पे और 4 ऊपर, so that is 8। इसको सॉल्व किया तो हमें फॉर्मल चार्ज मिलता है स्टूडेंट्स 0। सिमिलरली अगर आप बाकी कैलकुलेट करेंगे आपको ये ऑक्सीजन पे भी फॉर्मल चार्ज 0 मिलेगा और ये ऑक्सीजन पे फॉर्मल चार्ज मिलेगा -1। सो दिस इज हाउ स्टूडेंट्स वी कैलकुलेट फॉर्मल चार्ज। मूविंग अहेड स्टूडेंट्स, आई हैव रिटन सम एग्जांपल्स। आप इन एग्जांपल्स को प्रैक्टिस कर सकते हैं। यू कैन make their Lewis structure. You can try and find formal charge on all the atoms in the molecule. If you need a detailed answer for this, please comment karna and I'll share the answers for the molecules. Next students, we have some limitations of the octet rule. Let us understand what were the shortcomings, what were the limitations of octet rule. The first limitation student was hypovalent compounds or incomplete octet compounds. Octet theory couldn't explain why incomplete octet compounds are still stable. For example, BH2, BCl2, BH3, BF3, AlCl3. इनमें if you look at all the central atoms, none of the central atoms have 8 electrons in their valence shell. 8 इलेक्ट्रॉन नहीं होते हुए भी these are very stable. The second limitation is expanded octet or hypervalent compound, super octet. Atoms having more than 8 electrons in their in their valence shell. So if we take some examples, students, this is PF5, SF6. So for example, phosphorus over here has 10 electrons in its outermost valence shell. S में यहाँ पे there are 12 electrons. S over here has 10 electrons. So all this couldn't be explained by octet theory, that even though they have more than 8 electrons, how are they stable? Then Lewis octet theory couldn't explain what is called as odd electron molecules. Just as students, if you look at NO or NO2, they have odd electrons, but they are still stable. Why? This is a limitation. Finally, octet theory or octet rule, students, is based on the inertness of noble gases. That noble gases are inert because they have 8 electrons in their valence shell. However, we now know that even noble gases form compounds. So noble gas compounds couldn't be explained by octet rule. Octet theory or octet rule does not explain shape, stability and energy of molecules. So we wanted a new theory to really understand this, and these are the limitations of octet rule. Students, I would also recommend aapke short notes banao. You can copy these points and use these as short notes, just quick revision before the exam. Next we have, students, bond parameter. The first bond parameter that we will understand is called as bond length. Students, bond length is nothing but half the distance between the nuclei of a covalently bonded atom. इसे हम बोलेंगे covalent radius भी आप बोल सकते हैं. Similarly, we have something also called as van der Waals radius. So let's say we have two molecules. Let's say हमारे पास H2 और H2 के दो molecule है. Half the distance between the two molecules of H2, तो उस radius को हम बोलेंगे students van der Waals radius. एक और होता है metallic radius, and these parameters, students, हमने periodic table में भी किए हैं in detail. Next bond parameter that we have, students, is called as bond angle. Bond angle is nothing but the angle between the orbitals. So angle between the orbitals containing the bonding pair of electrons को bond angle बोलेंगे. एक example students हमने लिखा है यहाँ पे H2O, the bond angle in H2O is 104.5 degrees. Next students, we have bond enthalpy. Bond enthalpy means it is the amount of energy required to break 1 mole of bonds of a particular type between two atoms in gaseous state. For example, students, H2 diatomic molecule, let's say if I break the bond between H and H, the amount of energy that I need to supply to do that is around 435.8 kilojoules per mole. In case of polyatomic molecule, for example, students, let's say CH4 को आप break कर रहे हो, so you're going to break 4 bonds of carbon and hydrogen over there, then the average of that energy is called as bond energy or bond enthalpy. Next students, we have bond order. Bond order is the number of bonds between two atoms. For example, if I look at F2 में F and F के बीच में it's a single bond, O2 में it's a double bond, N2 में it's a triple bond. इसे हम covalence भी बोल सकते हैं students. The number of you can say that the electrons shared, जैसे यहाँ पे 2 electrons between F and F, each is sharing 1 each. यहाँ पे double bond 2 each और यहाँ पे triple bond 3 each. A very important point to note over here, students, is that as bond order increases, bond strength increases, bond length decreases, and bond energy increases. Next, students, we have the concept of resonance. What exactly is resonance? Students, sometimes a single Lewis structure cannot really explain the structure of a molecule. वहाँ पे एक particular molecule के multiple Lewis structures हो सकते हैं. These multiple Lewis structures, these canonical Lewis structures को हम बोलते हैं resonance or resonating structure. So students, the phenomena in which two or more structures involved in identical position of the atoms which can be written for a compound, these are called as resonance structures. For example, students, मैंने benzene के canonical और resonating structures लिखे हैं. दोनों structures का एक common hybrid होता है जिसे हम बोलते हैं resonance hybrid, which is the most stable form. Now students, resonance energy, the difference between the energy of the resonance hybrid and the most stable contributing structure को हम बोलते हैं resonance energy. हम bond order ढूंढ सकते हैं students by, if we know the different number of resonating structures, we can find bond order using the formula. It is the total number of bonds between two atoms in the resonating structures divided by the total number of resonating structures. So for example, students, यहाँ पे I want to find the bond order between sulfur and oxygen. तो यहाँ पे if I observe ये जो yellow bonds दिख रहे हैं, so between sulfur and oxygen in the first resonating structure there is a double bond. In the second resonating structure there is again a double bond, and in the third structure, students, I see that there is a single bond. So 2 plus 2 plus 1 number of bonds को sum कर दिया, divided by there are 3 resonating structures by 3, so the bond order is 5/3. Note, the stability of a molecule, students, is directly proportional to resonance. जितनी ज़्यादा resonating structure, उतनी ही ज़्यादा stability. More the number of covalent bonds, more will be the resonance energy. And the stability of a molecule is directly proportional to resonance energy. It is also directly proportional to the number of resonating structures. Next, students, we have dipole moment. Dipole moment या हम इसे बोलते हैं ionic nature of covalent bond. Students, no bond is 100% ionic or 100% covalent. There is some or the other character involved in each other. So first हम समझते हैं what is ionic nature of covalent bond. In case of heteronuclear molecules, let's say, students, there's a bond between hydrogen and fluorine. Now we know that fluorine is more electronegative. So what fluorine does is it pulls the electrons towards itself, and hence the electron cloud is closer to fluorine as compared to hydrogen. तो फ्लोरीन के ऊपर एक पार्शियल नेगेटिव चार्ज आ जाता है, हाइड्रोजन के ऊपर एक पार्शियल पॉजिटिव चार्ज आता है. दिस फिनोमेना इज कॉल्ड एज डाइपोल मोमेंट. इन केस ऑफ अ हेटेरोन्यूक्लियर मॉलिक्यूल, द इलेक्ट्रॉन पेयर शिफ्ट्स और इज डिस्प्लेस्ड towards the more electronegative atom. This resultant covalent bond is called as a polar covalent bond. Dipole moment given by the symbol mu, is due to polarization, the molecule possesses or it develops a dipole moment. Is dipole moment का value, students, is given by the product of magnitude of the charge into the distance between the two particles. इसकी unit is 1 dB. 1 dB in terms of electrostatic units is around 10 raised to minus 18, and in terms of coulomb meter it is 3.33 into 10 raised to minus 30. Dipole moment, students, is a vector quantity, तो वो हम vector law apply कर सकते हैं to find the resultant dipole. Next, students, we have some examples. This is very important because usually integer type questions यहाँ से बन के आ सकता है. You can have many questions in JEE and NEET on basis of dipole. I have written, students, all the examples over here जहाँ पे the net dipole moment is 0. Make sure, students, you copy all these examples. Next set of examples, students, जो मैंने यहाँ पे लिखे हैं, in these are very, very important trends in dipole. For example, if you look at the first one, NH3, students, has more dipole than NF3. दोनों का structure pyramidal है, but what happens in NH3 is all the dipoles are in one direction. As you compare that with NF3, यहाँ पे N and F का dipole का direction and the lone pair का dipole का direction is different, and hence the resultant dipole in NH3 is greater as compared to NF3, a very important example. I've also written some more examples, students. As we see that the electronegativity decreases, the dipole also decreases. एक अच्छा exception है the third one, students. Observe here, CH3Cl का dipole is more than CH3F, then CH3Br and CH3I. Some more examples. Make sure, students, you note this trends in dipole. I've given some homework questions. I want you to try these, arrange them in decreasing order of their dipole strength. And if you need hints and solutions for this, please let me know in the comment section. Next, students, what are the applications of dipole moment? Very important. The first important application is to find the polarity. Polarity, students, also tells you the actual structure of the molecule, the positioning of lone pairs, कि वो lone pairs कहाँ present है. So dipole will help us decide the polarity of a molecule. It helps us decide the geometry of the molecule. It also helps us decide the percentage ionic character. Next, students, we have the next theory to understand how molecules are formed is valence bond theory or VBT. Valence bond theory, students, says that the atomic orbitals, to form a covalent bond, they overlap each other. To form a covalent bond, overlapping takes place between half-filled valence shell orbitals. So let us understand, students, what's happening over here. If you look at the graph over here, we have two hydrogen atoms. Let us assume that they are hydrogen atoms. Students, when they are very far from each other, the potential energy of the system is almost zero. Now, when the atoms come closer, when the atoms come closer to each other, the potential energy of the system starts to drop, and the lowest potential energy of the system is when the molecules overlap and the amount of attraction, the force of attraction and the force of repulsion between the two atoms, they properly balance each other. It is that point when bond formation takes place. So for example, the bond length over here for hydrogen, as we see, 74 picometer. Bond enthalpy is also given, which is around 435.8. Now, students, let's say what if we force the molecules closer? मतलब 74 picometer से और close करने की अगर हम कोशिश करें, so what really happens is that the force of repulsions now start dominating the force of attraction, and यहाँ पे हमें दिख सकता है that the potential energy of the system shoots up. Basically unstable कर रहे हैं हम. Okay, so this is a very important plot. Now, students, I have given some important points regarding the strength of different overlaps. अभी next slide में हम overlapping के बारे में पढ़ेंगे, but these points are also very important. Make sure you note them down. Next, students, we have different types of overlapping. Overlapping results in formation of two types of covalent bond. The first type of covalent bond, students, is called as sigma bond. sigma bond is formed due to axial overlapping. It forms due to head-on overlapping. जैसे हमने अभी हाइड्रोजन का एग्जाम्पल पढ़ा स्टूडेंट, SS ओवरलैप, HF का एग्जाम्पल आप ले सकते हैं which is SP overlap. All result in the formation of sigma bond. यहाँ पे PP overlap taking place along the axis. This results in the formation of a sigma bond. So a sigma bond is due to end-to-end overlap, along the axis overlap. Sigma bonds, they do not participate in resonance and there is no free rotation around the sigma bond. Students, free rotation आपने conformation isomerism में पढ़ा होगा in organic chem. Now students, when orbitals overlap sidewise, we get what is called as a pi bond. So it is formed by sidewise or lateral overlapping of the orbitals. यहाँ पे students हम देख सकते हैं p orbital when they overlap sidewise we get pi bond, and यहाँ पे हमने एक p pi d pi overlapping भी बताया है. और again pi bond participates in resonance but there is no free rotation around pi bond. Next students, we have the concept of hybridization. So the concept of hybridization says that the atomic orbitals, they mix it together and they get new geometry, new shape. That is called as hybridization. So let's understand the different types of hybridization. The first hybridization students that we have is called as sp hybridization. So यहाँ पे हमने एक example लिया है of beryllium chloride, BeCl2, beryllium dichloride. So if you see students, सबसे पहले बेरिलियम का ग्राउंड स्टेट लिखा है. वन इलेक्ट्रॉन फ्रॉम हियर इज एक्साइटेड टू द 2p ऑर्बिटल, इसे हम कहते हैं एक्साइटेड स्टेट, एंड द टू ऑर्बिटल्स हाइब्रिडाइज, द टू एटॉमिक ऑर्बिटल्स 2s एंड 2p हाइब्रिडाइज टू फॉर्म अ हाइब्रिड स्टेट, इसे हम बोलते हैं sp हाइब्रिडाइजेशन. The geometry is linear and the bond angle is 180 degrees. The number of sigma bonds are 2. Students, VCl2 in case of solid state, so gas में it is sp hybridized, but solid state में क्या होता है, ये जो unhybridized orbital हैं they are used and it forms what is called as a trimer. So trimerization होता है. And not only in VCl2 students, आप एक और example ऐसे याद रख सकते हैं. For example, there is also dimerization in AlCl3. AlCl3 in gaseous state we can say that it is sp2 hybridized, but in solid state it becomes sp3 hybridized, and again there is dimerization. One more example students, that was sp. Next example हमारे यहाँ पे है sp2. example हमने लिया है beryllium, boron trichloride. Next example students we have is sp3 hybridization. थोड़ा वैलेंस शेयर इलेक्ट्रॉन पे रिपल्शन थ्योरी भी मर्ज कर दिया है, because if we see in CH4 hybridization is sp3, geometry is tetrahedral. But the same if you observe in ammonia, though the hybridization students is sp3, due to the presence of one lone pair the geometry here becomes trigonal pyramidal. And over here, due to lone pairs, two lone pairs, यहाँ पे geometry becomes bent or V-shaped. Now students, why is this happening? And the reason for this is new repulsions coming in. So यहाँ पे students, there is lone pair repulsion, lone pair bond pair repulsion, and bond pair repulsion. Here there is lone pair bond pair repulsion and bond pair repulsion, and in CH4 it is only bond pair repulsion. Next we have students one more example, जैसे कि I have given C2H4, यहाँ पे hybridization is sp2. remember that in a double bond one is sigma and the other is pi. Next students, यहाँ पे in ethyne I want you to tell me in a triple bond how many sigma bonds are there and how many pi bonds, and also tell me what is the hybridization of ethyne. Please share your answers in the comments. Next we have students some more examples यहाँ पे. For example, phosphorus pentachloride PCl5. PCl5 का students the geometry, the hybridization is sp3d and the geometry is trigonal pyramidal. Now I'm sorry, trigonal bipyramidal. Students, pyramidal. Second point that students I want you to remember here is that the electronegative atoms, will occupy axial positions, they won't occupy equatorial positions, and the reason is yahan pe Bend's rule. Second, students, remember that axial bonds length is bigger, so you can say the bond strength is less as compared to the equatorial bonds. SF6 we have, students, over here, this is octahedral in geometry, and the hybridization, students, over here is sp3d2. how we get ground state, excited state and the hybrid state, iska bhi explanation yahan pe side mein diya hai. Next, students, we have is the valence shell electron pair repulsion theory. This is very simple to understand, students. Because of lone pairs, the geometry changes and the shape, फिर हम shape बोलते हैं अभी molecules का, because the geometry changes. यहाँ पे, students, depending upon the number of bond pair and the number of lone pairs, we have different shapes of the molecules. Let's take an example. For example, in the first case, students, we have टू बॉन्ड पेयर एंड वन लोन पेयर. जैसे कि SO2 का आप अगर एग्जांपल देख ले, SO2, स्टूडेंट्स, इज अ बेंड मॉलिक्यूल. अमोनिया, 3 लोन पेयर एंड 1 बॉन्ड पेयर. So though the hybridization is sp3, but the geometry becomes, so the geometry is tetrahedral, the shape becomes trigonal pyramidal. Next, students, if we have 2 bond pair, 2 lone pair, तो वो water हो जाता है, the geometry becomes, the shape becomes bent. Next, if we have, जैसे कि यहाँ पे H2O का एग्जांपल लिया है. नेक्स्ट, इफ यू हैव 5 सिग्मा बॉन्ड्स होते तो दैट वुड हैव बीन ट्राइगोनल बाइपिरामिडल sp3d. बट 4 बॉन्ड पेयर और एक लोन पेयर अगर आ गया, then the shape becomes seesaw. The example is SF4. Now, students, एक और if we have 3 bond pairs and 2 lone pairs, and the shape becomes T-shaped. So what we observe is एक bond pair निकल रहा है and एक lone pair आ रहा है. Let's go to sp3d2. Now sp3d2, students, SF6 was octahedral. However, let's say if I remove one bond pair and make it one lone pair, so 5 sigma bond but 1 lone pair, then the geometry becomes square pyramidal. Now I remove one more bond pair, usko lone pair kar do, so 4 bond pair and 2 lone pair, the geometry becomes square planar. मैं एक और एग्जांपल देता हूं, स्टूडेंट्स, where in SF6 we have 6 bond pair and 1 lone pair, the geometry becomes distorted octahedral. So this valence shell electron pair repulsion theory helps us understand, students, that because of the lone pair repulsion, how the geometry of the molecule is affected. Moving ahead, special bonding cases where, students, we have the example of diborane over here, which is formation of what is called as banana bonding. So what we observe here in diborane, students, is that here boron and hydrogen, 3 centers are sharing 2 electrons. This is called as 3 center 2 electron bond. ये जो नीचे का bond भी है ना, students, this is also a 3 center 2 electron bond. And जो yellow bonds मैंने बनाए हैं, students, these are 2 center 2 electron bonds. The banana bonds or the 3 center 2 electron bonds are perpendicular to the plane. Similarly, ये structure को आप ऐसे भी बना सकते हैं. There are many more examples, students. For example, B2H4, आप Al2H6 ले सकते हैं. All these also contains these bridging bonds or these banana bonds. Very important. Next, students, we have the phenomena of what is called as back bonding. Now, students, if you remember BF3 was sp2 hybridized and an incomplete octet. But what happens here is, in the empty or the unhybridized 2pz orbital, fluorine, say boron, borrows electron. This phenomena is called as back bonding. Because of this, you can say that there is like a partial double bond character between boron and fluorine. And if we understand, if we look at the strength of Lewis acid, BF3 has the best back bonding, इसलिए वहां पे उसकी acid strength decreases. Bi3 has very poor back bonding and hence it has and hence it's more acidic compared to the other compounds. Some more back bonding examples I have written over here, students. Cl2O, a very important example here. If you look at the bond angle reason over here, 110, you can say approximately 111 degrees, 104.5 and 103, because of the presence of back bonding in Cl2O. Similarly, trissyl oxide, though it is sp3 hybridized, it is linear due to back bonding. Similarly, trisylamine is pyramidal in geometry. Pardon me, trimethylamine is pyramidal in geometry, but trisylamine is trigonal planar in geometry, again due to back bonding. And finally, back bonding also affects acidity. For example, R3SiOH, there is back bonding between silicon and oxygen, hence it is more acidic as compared to this alcohol. Next, students, we have a very important theory which is called as molecular orbital theory. Now, molecular orbital theory, students, says that the atomic orbitals, when they overlap with each other, they lose their original identity, and what they form are called as molecular orbitals. And when they overlap, there are two types of overlap. The atomic orbitals will either overlap in phase, or the atomic orbitals will overlap out of phase. When the atomic orbitals are overlapping in phase, it results in the formation of what is called as the bonding molecular orbitals. And when they overlap out of phase, it results in what is called as the anti-bonding orbitals. Anti-bonding molecular orbitals have higher energy and lower stability as compared to bonding molecular orbitals. Now, here, students, we can see that 1s orbitals overlapping in phase to form sigma 1s, which is bonding molecular orbital, and here they are overlapping out of phase to form anti-bonding molecular orbital. And what we have, students, here is also called as a node. I hope everyone remembers from atomic structure what is a node. Similarly, 2p, students, forming bonding molecular orbital, anti-bonding orbital with a node, and p orbital again can form when it overlaps sidewise bonding pi molecular orbital and bonding and anti-bonding molecular orbital. And here, students, there are two nodes. Now, all these diagrams are very, very important. Next, students, we have the increasing order of the energies of molecular orbital. Here we have to be very careful because there are two orders that we need to remember. In case for oxygen and fluorine, or where the number of electrons are greater than 14, the molecular orbital energy follows the trend which is mentioned here. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and then comes sigma 2pz. But for the number of electrons which are less than 14, Li2, Be2, B2, C2, N2, this is the particular order which is followed. And students, you have to be careful over here, because here pi 2px2, pi 2py, pi 2px and pi 2py have lower energy as compared to sigma 2pz. Next, we also have something called as bond order. Students, bond order is defined as the number of electrons in bonding orbital minus the number of electrons in anti-bonding orbital divided by 2. If there are unpaired electrons, paramagnetic. If there are paired electrons, then it will be if there are paired electrons or no electrons, it will be diamagnetic molecule. So let's take an example. Let's understand C2 and how do we write the molecular orbital configuration. C2, student, electronic configuration. C2 will have 12 electrons. So sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. इसको हम K and K star भी लिखते हैं, students. So we are done with 8 electrons, but it is 12 electrons. So next we write over here is pi to p x1, pi to p y1. Remember, you will fill them one at a time. So 2, 4, 6, 8, 9, 10, 11 and 12. I repeat, students, you fill one at a time, and then we are just following Hund's rule over here. Then N2 will have 14 electrons. Let's try and fill that, students. So 2, 4, 6, 8, 9, 10, 11, 12, 13 and 14. Next, students, in O2 we have to be careful over here, because sigma 2pz will come first, and O2 will have students in total of 16 electrons. So 2, 4, 6, 8, 9, 10, 11, 12, 11, 12, 13, 14, and then students pi to p, pi star to p x1 and pi star to p y1. Using the formula we can also calculate their respective bond orders. चलो ऊपर वाले का बॉन्ड ऑर्डर कैलकुलेट करके देखते हैं. बॉन्ड ऑर्डर का फॉर्मूला था हाफ इनटू नंबर ऑफ इलेक्ट्रॉन्स इन बॉन्डिंग ऑर्बिटल. सो 2, 4, 6, 8. I see 8 electrons minus number of electrons in anti-bonding orbital 2, 4. So यहाँ पे bond order मिल जाएगा students 2. Let's quickly calculate the bond order. Over here we have 2, 4, 6, 8, 10. So 10 minus, and we have over here 2 and 2, 4. So the bond order will come as 3. I want you to find the bond order of O2 and please put that in the comment section. Next we have student what is called as hydrogen bonding. So hydrogen bonding student is a force of attraction between hydrogen atom with an electronegative atom such as fluorine, oxygen and nitrogen. There are two types of hydrogen bonding: intermolecular hydrogen bonding and intramolecular hydrogen bonding. Next people, intermolecular hydrogen bonding is bonding between the same atoms of the same molecule और atoms of different molecules. जैसे हम homo internuclear भी बोलते हैं, hetero internuclear भी बोलते हैं. I've written the H2O and HF का example and यहाँ पे hydrogen bonding between alcohol and water. Next we have students intramolecular hydrogen bonding. So intramolecular hydrogen bonding is hydrogen bonding within the molecule. So for example over here orthonitrophenol, salicylaldehyde, orthofluorophenol. There are many examples more students. Salicylic acid, chloryl hydrate is a good exception. Though chlorine should not show hydrogen bonding, there is intramolecular hydrogen bonding in chloryl hydrate. Next students we have the effect of hydrogen bonding on physical properties. Alcohol is soluble in water because it forms hydrogen bonds with water. Orthonitrophenol is steam volatile as compared to paranitrophenol because of intramolecular hydrogen bonding. As the number of hydrogen bonds increases, viscosity increases, melting and boiling point increases because of hydrogen bonding. H2O is a liquid, H2S is a gas. Again, this is because of hydrogen bonding. So hydrogen bonding affects many physical properties. Make sure you copy all these down and copy the examples. Next we have students final electrovalent bond or ionic bond. Start of the lecture we know that electrovalent or ionic bond is formed by transfer of electrons, but there are three important factors which decide the strength of an ionic bond or which decide the formation of an ionic bond. It is ionization energy. So lower the ionization energy, quickly it will form a cation. For the anions should have high electron affinity, and very important we have something called as lattice energy. So what exactly is lattice energy? Lattice energy is the amount of energy required to completely separate one mole of a solid compound into its gaseous constituent ions. The lattice enthalpy or lattice energy is directly proportional to the magnitude of charge on the cation and anion, and it is inversely proportional to their size. Just like students, we have ionic nature in covalent bond, we also have something called as covalent nature in ionic bond, and this is also called as polarizability or polarization, and this is decided by Fajan's rule. So the ability of a cation to polarize an anion, what that means is cation because of its high charge density attracts the electrons of the anion. It distorts its spherical shape, and it is as if the cations and anions are sharing electrons. This is called as covalent nature of ionic bond. So this polarization is directly proportional to the covalent character, and the magnitude of polarization depends on rules which are given by Fajan. So let's understand what these rules are. Polarization is directly proportional to inversely proportional to the size of the cation. It is directly proportional to the charge on the cation and anion, and very important students, ions which have pseudo noble gas configuration. For example, if I compare CuCl with NaCl, CuCl is more covalent character because of pseudo noble gas configuration of Cu plus as compared to Na plus. Okay, students. So this completes all the important points which are required for chemical bonding. I would request everyone to make good short notes, copy all these points, or what we can do is you can always quickly go through the lecture. Let's say if you have a test coming up, this will help you quickly revise the chapter within half an hour. If this lecture was helpful, I request everyone to please like, subscribe and share the video. Thank you so much from JP's Academy. Thank you so much.